Okay, let's go and get started. Today we're going to be talking about storage classes and storage modifiers in C. And really there are going to be two lectures today, class 20 and class 21. I'm going to double those up today. So make sure after you watch this one to watch the next one that's posted as well. All right, let's go ahead and get through this one. All right, so essentially what a storage class is, it's the storage class of a variable defines the scope and duration of that variable, or the scope and lifetime of that variable. And essentially, this is something you're probably used to from other programming languages, but scope is where a variable is visible or active within the code. So in other words, the scope of a variable is where you can access it. The lifetime of a variable, or the duration of it, is how long the variable remains active in memory. In other words, how long does it retain a value? Not necessarily where you can see it from or from where you can see it, but how long is it actually holding on to a place in memory that's storing that value. And together, that scope and lifetime defines what we would call a storage class. Now, let's look at an example that illustrates the different storage classes that are available in C. And so here's some example code, and notice it's not really a complete working thing. It's just kind of some, it is syntactically correct, but I have this code goes here. So we're not really doing anything with the variables, but let's go through the different storage classes that are in here one at a time. So first off, this line up here, I have this unsigned int called ErrorCount. Notice that is declared outside of a function. It's declared kind of up here on its own. That makes that a global variable. And a global variable has a lifetime of what we would call application lifetime, meaning that that variable, since it's a global, it'll hold on to its value as long as the application is running. When the application ends, that's the only time that that variable will go away and stop holding that value. And the scope of a global variable is application as well, meaning any code that is in our project can actually access that global variable. It's accessible from not just the source file that it's in, but any source file. Now there is a little caveat for what we have to do to be able to access that in other source files other than the one it's declared in. We'll talk about that a little bit later on today. Now the second one here, right below that, is this one. Notice it looks just like this one up here, except it has the word static in front of it. That makes this what's called a file scope variable. And that current users variable that we have there is a file scope variable, meaning that its application is still lifetime, just like a global, but its scope, the place that can see it, are only other things that are in this file. In other words, if I had another source file, it could not access this variable. It's kind of like, think of it like a private variable that can only be accessed by the rest of the code in this file. And that can be useful for making something a variable that's shared between different functions, but is private to that library or that file that's actually using it. Globals, however, are kind of like public, and they can be accessed from anywhere. Okay, now we have some local variables. We have two variables I. These are different even though they have the same name. This is the I variable inside of main. This is the I variable inside of this function f1. Those are both locals. They both have a function lifetime, meaning when this function returns, the variable goes away. When this function f1 returns, that variable goes away. It only holds a value while that function is running. And the scope of that is called block scope, meaning that it's within the block of this function body is where that is visible. In other words, between that curly brace and that one, where we can access this integer I. And in this one, it's a different variable, different integer I, only accessible from that curly brace inside of that one. In other words, if I had some other function, I tried to access variable I, unless it had a local, it could not see either of these. They're only accessible from inside of that block itself. Now there's one other one here, and that's this call count down here, the static int down here. That's a local static variable. And local static variables have a scope that's the same as a local variable up here, block scope, meaning it's only accessible from inside this function. But they have this unique property that allows them to have a lifetime of application lifetime. In other words, even though this variable is only accessible inside of this function f1, it'll hold on to its value from one time we call the function to the next time we call it. In other words, you could make a variable that keeps track of its value, holds on to its value from one function call to the next. It'll remember something from the previous time you called the function. And that can be useful for things like you want something to initialize and only run once. You can make a variable inside of it that starts out at 0, like we have here, and then we could increment it, and then the next time we could say, oh, if it's greater than 0, we know we've already ran this once. So you can make a function keep track of how many times it's been called, like a function that counts up a number of errors or something like that. Static variables can be useful for making something that keeps track, or maybe the depth of recursion. Every time you call the function, you increment it. Anytime you return from the function, you decrement it. You can see how deep into that how many levels of depth you've called that function to know how deep you are into that. So statics can be useful because they hold on to their value. They also can be useful because even if I don't say equals 0 here, they're initialized to 0 automatically, where local variables can have just garbage values in them. Okay, so a couple of keywords that are associated with a lifetime. Static, which can make a variable with a fixed lifetime. Automatic, which can make a variable with an automatic lifetime. Now, one of the things about these static we already saw in the previous examples, but automatic variables you don't see the automatic keyword used very often, and that's because the default for local variables is that they're automatic. So why specify it, why type in the extra word automatic when it will just default to that? So you don't see it used very often. But static you will see used, and that makes a variable so that it retains its value in memory until the application terminates. All right, so let's look at each of those in a little bit more detail. So there are 4 types of scope. Program scope, which are what global variables are, also sometimes called application scope. And those variables are declared outside of a function body without the static keyword on it. A file scope variable is one that is declared outside of a function body, but declared with a static keyword in front of it. And those are what are called file level variables, or file scope variables. And then function scope, the function scope in C is a little bit unique. It's only for labels that are inside of a function. In other words, you cannot make a function that jumps with a go-to statement from one function to another function. So that's function scope. And then block scope is what we saw with local variables, whether those are static or whether those are automatic. Those are all block scoped. And parameters also. So the parameters in a parameter list for a function, those are also block scope. Now, scope variables can have the same name as long as they're declared within a different scope. And the different scope could be within a different function, could be within a different file, could be one's a global, one's a local. But if you do have the same name for 2 variables where the scope overlaps, like a global and a local, it'll use the more recent or narrower scope. In other words, it'll use the local scope rather than the global. Function parameters always have a block scope and a function lifetime. No matter what you do with those, they always have that. And one quick bug warning here is that if you look at the keyword static, it actually has a dual meaning. In other words, when it's used inside of a block, in block scope, like a local variable that's declared static, it'll have block scope and application lifetime. And when it's used outside of a block, it'll have kind of, there's actually a typo here. Let me fix that real quick. Okay, so when it's used outside of a block, it'll have file scope and application lifetime. So in other words, static has 2 different meanings depending on the context of where it's used. If it's used inside of a function, it just changes the lifetime of the variable. If it's used on a global variable or outside of a block, then it changes the scope of that to being file scope rather than application scope or global scope. And so let me just switch back a couple pages here and look at that. So here's the example code. Notice this up here, there's static restricting the scope of this to be file scope from global, but then static down here is changing the lifetime of this to be application rather than automatic lifetime. Okay, let me pause for a second and I will be right back. Okay, now, as a quick reminder where we just came from here. Oops. We were just talking about scope and talking about if scopes overlapped, then it takes the narrower one. So in other words, you have two variables of the same name that are both in scope. One, for example, that's a global or a file level variable, and one that's a local. The local will take precedence in that scope that it's in. Now, there's another thing that we need to talk about too with respect to this, and that's what's the definition, the difference between what are called definitions or declarations and allusions. So a definition or a declaration actually allocates space for a variable. So for example, you have like int I, that's a definition. If you have a global like int num underscore players, that's a definition. So when you have a definition, that's an actual allocation of space for a variable. An allusion, on the other hand, is essentially a way to tell the compiler the name and type of a variable that you're going to use, but it's allocated somewhere else. And really, those are only used for globals. So if you have a global variable that is defined in another file, and you want to use it in a different source file, then you need to have an allusion to that in the source code that's using it. And the allusion is really just a way to say, hey, compiler, there's a variable that's defined somewhere else. This is its type, and this is its name. And to use that global variable that's defined in some other, somewhere else in a source file that we're in, we use a special keyword called extern. And basically, we just say extern, give the type of that variable, give the name of the variable, and that's telling the compiler, hey, this file I'm compiling now, and I'm going to use this variable that's external. Extern stands for external. That's external to the file that I'm in now. It's somewhere else that it gets defined. And then when the compiling process goes to the linker, it'll tie in all of the externs with the actual place in memory where those are stored. But we need to declare them as extern. And if you're coming to this from Python, you can think of it a little bit like using the keyword like global inside of a function to say, hey, there's this global variable that's somewhere else and I want to access it. So think of this as saying, hey, there's a global variable that's external to this source file. Here's its type. Here's its name. I'm going to use it here, though. And this gets more and more important when you have large projects where there are multiple global variables that need to be they're defined in one file, need to be accessed in a different file. And so this is an important thing for larger projects when you get to them. And a lot of times you'll put that extern thing into a header file. All right, now there's another special kind of storage modifier called register that you can put in front of a definition. And what a register variable is, when you say register, for example, register int I equals 0, that works just like declaring an integer I equals 0, but what it's telling the compiler is we're saying, hey, I want you to know that if at all possible when you create the machine code for this, just store this variable I in a CPU register rather than storing it in memory with the other variables. And the main advantage of that is for optimization. So for example, if you store a variable in memory, whenever the system, the CPU needs to access it, needs to go out over the address bus, pick up that variable, bring it into the CPU to use it. Where if you declare that variable as a register variable and the compiler can accommodate that, then you are basically just saying, hey, use this register that's already in the CPU to keep track of this variable. And that can save a lot of having to pull things from memory, put them back in memory, pull things from memory, put them back in memory, which can result in code, CPU machine code, that is much faster for certain kinds of operation. Now, mostly that register variables are used for you have some kind of loop that needs to compute something really quickly rather than using things that are stored in memory. Just sticks a couple things in registers, and that can make code a lot faster. Now, the compiler isn't obligated. There's a cat fight, sorry. There's a kitten, and he keeps trying to play with the grumpy cat. So if you hear noises and crashing, then that's what that is. But the compiler is not obligated to use registers. You're just saying, you're kind of giving it a hint saying, hey, if at all possible, and there are registers available, generate the machine code that puts these variables into a register. And if you have too many register variables that you declare, the CPU, it depends on the architecture on, but there's a limited number of CPU registers. So it might not be able to obligate that. But in most cases, if you have one or two of these, maybe even 3 of them, depends on the architecture, but it might be able to do that, and that could result in a speed up of your code. Okay, another modifier is the const modifier. What that is, so again, you put that before like the other one, so const, and then the rest of the variable declaration or definition looks the same. And what that is that's telling the compiler to ensure that that variable's contents are not to be modified. Don't let any code modify this. It's a constant. So the compiler will then, after you declare a variable as a const variable, it'll basically say, if you try to access that and change that, the compiler won't let the code compile. So for example, here's like a const double type called pi, and you don't want to have the code accidentally change that somewhere or have the programmer change that. You want it to be constant. So this is actually creating a variable, a double precision variable, sticking this number in it, and we're making that constant, so it can't be changed. And things like that can be useful. You might also have use const on function parameter types to say that this function is not going to change this thing that's passed in. And that's used a lot when you pass a const pointer to something. Speaking of which, bug warning here. If you do int pointer const like this, that's saying that the pointer value is constant. It's saying an integer pointer that is constant. In other words, the address is not going to change. If I say int const pointer, that's saying the data pointed to is constant. So in other words, don't let the data that this points to be changed. So this has a subtly different meaning, and there's a bug warning there where some people will do this one thinking that that means the data can't be changed, but they're really, or doing this one where they think that means the data pointed to can't be changed, but we're really making it so the pointer can't be changed. So just watch out for these 2 variations of that. Okay, another modifier is the volatile modifier. This one is especially important if you're doing low-level systems programming like an embedded system or an operating system. And what volatile does is you basically just put it as a prefix like the other ones. And what volatile is it says, hey, compiler, when you go to use this variable, always go to memory to get the value. And if they change the value, always put it directly back in memory. And the main reason why that's important is if you have an optimizing compiler, it might say, oh, you picked up that value from memory and then you changed it. I'm just going to keep that in a register here temporarily. But if you have a variable that needs to be, like let's say a global that's shared between 2 different processes, like maybe an interrupt, like you press a key on the keyboard and you want it to update the last key that was pressed every time a key on the keyboard gets pressed, you want it to update that variable so some other part of the program can see that value change when keys are pressed. Well, if you have that cached in a register because the optimizer decided it would be faster to do that way, you could be typing keys and it would never actually change this other place in memory. And so what volatile does, it says, don't optimize this into a register. Always get it from memory. When it's changed, always put it right back in memory as soon as you're done. And I've run into a lot of bugs on the embedded systems kind of programs that I write where some programmer did not know to make something volatile that was shared between 2 processes, or something that was modified in a like a timer interrupt that ticks and updates something, or in some I/O interrupt when you receive a wireless packet, update these things so that the rest of the program can use that wireless packet. Well, if you don't use volatiles for those things, it could change it in one place and you would never see it update in the other place. So this can be an important one, especially for low-level systems programming. Now, you can also combine those modifiers. So you could make an extern volatile, an extern const. You could make a const volatile, although that doesn't make any sense to do that. But you can mix and match those modifiers to make things that have multiple ones of those attributes. Now, one thing to note is with, and I mentioned this earlier, the extern statement is often placed in the header file for whatever .h file, the library is for something. So for example, the Windows sockets library to let you talk over TCP/IP from one machine to another machine. That has some global variables, but you don't need to put an extern in your code to do that. You just have to include the winsock.h or whatever in order to access those. So as soon as you include that, it has the extern built inside of the header file. So now you can access those global variables without having to do it explicitly. So that would mean that a source code that you write that wants to use that library and use that thing, just have to pound include the thing. And you should do that, pound include the header file. And you should do that with your own stuff if you have globals that need to be shared. Put the extern declaration inside of the header file. Put the actual variable declaration inside of the .c file for it. Don't put the variable declaration in the .h file, only the allusion to it. Okay, that's all for now, but there's one other video I want to do today as well, so look for the next one. I went ahead and put that under class 21, but I wanted to also get in dynamic allocation. There's some stuff I want to make sure I get covered and make sure you're exposed to before you head off for Thanksgiving break, especially since we have to have our paper part of the exam for that, so we're going to double up the videos today. This one hasn't been too long. We've only been 20 minutes into this. So I'm going to go ahead and stop this video, look at the next one on dynamic memory allocation. We're going to do some coding in that one. All right, so I'll see you in just a couple minutes.